Welcome to this next video in the playlist on group theory. In this video, what we're going to discuss is composition series and the Jordan-Hőlder Theorem. Okay, so we'll begin with composition series and then we'll move on to the Jordan-Hőlder Theorem. Okay, so let's begin with the motivation for composition series. What are we actually going to be doing here? Well, in this video, previously in this playlist on group theory entitled Simple Groups, I say in that video, although I don't really give an explanation for this, that all finite groups can essentially be thought of as being built out of finite simple groups. And in this video, what we're going to do is add some meaning to that. We're going to explain what I actually mean by that, how, in a sense, you can think of all finite groups as being built out of finite simple groups. Okay? And we're going to do this through composition series, and then what we will prove about composition series via the Jordan-Hőlder Theorem. Okay, so now let's move on to the actual definition then of a composition series. Now the definition of a composition series doesn't require the group that you are working with to be a finite group. It applies for infinite groups as well. It's just that in the case of finite groups we can guarantee that you will actually have a composition series, as I'll show you in a moment. Okay, so let's start off then with the definition of a composition series. So a composition series is fundamentally an ascending chain of subgroups that obey some additional properties that I'll show you in a moment. Okay, but that's the starting concept that we need to get across, that it is an ascending chain of subgroups, also known as a subgroup series. Okay, so let me show you what I mean by this. So what we're going to have is our group capital G here, and as I say, this could be a finite group or it could be an infinite group. Okay? What do I mean by then an ascending chain of subgroups? Well, an ascending chain of subgroups is a series of subgroups that are all nested inside one another. So what you do is you start off with the trivial subgroup, which I'll denote by 1 here, and then what you do is you find a larger subgroup that obviously will then completely contain the trivial subgroup. Okay, well actually firstly we often give the trivial subgroup another name. We give this G0. Okay, so G0 is just going to denote the trivial subgroup, so I'll underline them in the same colour. These are just different notation for the same thing. So we'll call the trivial subgroup G0 just so that it fits into the pattern. And then what you're going to do is you're going to find another subgroup that's bigger than this one. Okay, so it's going to properly contain the trivial subgroup. Okay, so note I haven't put that is less than or equal to, I've just put is the strict less than. So this is going to be a proper subgroup of the next one along, which we'll call G1. Okay, and then we'll go on. Okay, we'll go up. And then we'll all go all the way up to what I'll call GK, and GK is going to be our other notation for the entire group capital G. So I'll underline this in orange. Okay, so this is what I mean by an ascending chain of subgroups, a bunch of nested subgroups, one inside of the other, and they're all properly containing the one that goes before them. Okay, so let's just draw a picture for this then. So let's have our entire group represented by this box here. Okay, so this is the group, and I'll colour the, or rather outline the group in orange, like so. Okay, and then we start off with the trivial subgroup, which is of course the smaller subgroup. So we'll have the trivial subgroup shown by this tiny little box down here. Okay, and that will obviously just contain a single element, which will be the identity of our group. So here is what we could call either 1, or we can call it G0. Okay, and likewise, actually, we're going to call G here GK, so that it fits into the notation of the groups involved in this ascending chain being labelled G index a number. Okay, and then what we're going to have is we're going to have lots of subgroups that gradually get bigger and bigger. So we're going to have one that now properly contains the trivial subgroup here, and this is going to be G1. Okay, so let me colour this one in as well. So here now you can see that the trivial subgroup is properly contained in this, so this is going to contain elements that are not in the trivial subgroup, okay, and it's going to be another subgroup of capital G, okay, but a bigger one now. Then what we can do is we can find an even bigger one, so that now contains G1 properly. Okay, so here now this next one is going to be G2, and what colour should I do G2 in? We'll do it in yellow here. Okay, so here's the next one up, G2. So again, we've gone one step bigger. We found a bigger subgroup of capital G that properly contains the one that went before, and therefore will properly contain all of the ones before it, because the one before contained the one before, etc., etc. Okay, then what we'll do is we'll find an even bigger one. So let's now go to this one here, and let's say this is G3 here. Okay, so what colour shall I go to now? I'll do it in vivid purple here. So here is G3, and let's say we go one more. Okay, so we'll go now up to G4 then on this picture, which will be this entire half. Okay, so here then is G4, and then GK, the final improper subgroup, would then be G5. So in this picture, this will be called G5 here. Okay, and we'll have the final one coloured in red here. So this is G4 here, or the penultimate one rather, before the improper subgroup. So there in picture form is the concept of a subgroup series then. So I'll write down that key word here, or that key expression, subgroup series. So a subgroup series is just this ascending chain of subgroups that all properly contain the one that went before them. Okay, and it's this chain that will eventually get to the improper subgroup. So it's a chain of subgroups that are in between the trivial subgroup and the improper subgroup. Okay, so that's the concept of a subgroup series. Now, we're going to go one step up from this, okay? We're now going to talk about the concept of a subnormal series, because a composition series is going to be a special type of subnormal series. Okay, so we've gone from subgroup series to subnormal series, and then we'll go another step up to composition series. Okay, so before I can define composition series, let's just define what a subnormal series is. Okay, so a subnormal series is a subgroup series, but in addition to just being any old subgroup series, it has to be the case that each one of the subgroups in this subgroup series has the subgroup before it as a normal subgroup. It has to be the case that GI is a normal subgroup in GI plus 1. Okay, so we could replace all of these symbols here now with normal subgroup symbols, and indeed I'll just do that in a moment. Okay, so I'll do it here. So we'll have G0, which is still our new notation for the trivial subgroup. It will be a normal subgroup inside G1, which will be a normal subgroup inside G2, and this will go on all the way up to, GK minus 1 will then be a normal subgroup inside GK, which will be denoting our improper subgroup here. So here then is our subnormal series. Now note, I am saying that this one here, GI, has to be a normal subgroup inside GI plus 1. So G0 has to be normal inside G1. G1 has to be normal inside G2. It does not mean that every single one of the subgroups in this subgroup series has to be normal inside the entire group. They have to be normal in the one that's above them, okay? And that is a different thing to being normal in the entire group, okay? So the trivial subgroup will have to be normal inside G1. G1 will have to be a normal subgroup of G2, but that doesn't necessarily mean it's a normal subgroup of the entire group, capital G. It means that if you conjugate it by anything in G2, it'll remain fixed, okay? So don't think that this means all of these subgroups in a subnormal series have to be normal in the group capital G. They have to be normal in the one above them in the subgroup series, which is a weaker condition than being normal in the entire group. And we know that even though we've got this chain of normality here, that doesn't imply that each one of these is going to be normal in the entire group. Okay, so remember, if K is normal in H and H is normal in G, it does not imply that K is normal in G. It has to be the case that K is characteristic in H and H is normal in G. And I'll write this down rather than just shouting it at the camera. Okay, so if K is normal in H, okay, and H is then normal in G, it does not imply that K is a normal subgroup of G. If you had the stronger condition that K was a characteristic subgroup of H, the better version of being a normal subgroup fixed by all automorphisms rather than just all inner automorphisms, then you can conclude that K is normal in G, but not just with K being normal in H and H being normal in G. Okay, so even though this is true, you cannot conclude that G1, G2, all of them are normal in the entire group. Okay, so do understand that that's a weaker condition than all of these subgroups being normal in the group capital G. Of course, if they are all normal in the group capital G, then you're done. It will be a subnormal series in that case, because if it's normal, if each one of these is normal in G, then they'll certainly be normal in a subgroup of G. Okay, but in general, a subnormal series is weaker than all of the constituents of the series being normal subgroups in the group capital G. So there's the concept of a subnormal series. So let's now go up another step, up to the concept then of a composition series. Okay, so a composition series then is a subnormal series, but in addition to having this normality criterion, it also has to be the case that if you quotient gi plus 1 out by gi, and let me just add on to this, this has to be the case for all I is equal to 0, 1, all the way up to k minus 1. Just add that little qualifier in there. So all of them have to be normal in the one above them. Okay, now what that means, if we've got a subnormal series, of course what we can do is we can quotient the one above you out by the one below. Okay, so we can do gi plus 1 quotient out by gi for each of these. So we could do g1 quotient out by g0, we could do g2 quotient out by g1, g3 quotient out by g2, all the way up to gk quotient out by gk minus 1. Okay, so we can quite happily ask about this. And in order for this to be a composition series, in order for this subnormal series to be gifted with the title of being a composition series, these quotient groups that you construct have to be simple, okay, are simple groups. Okay, and that must be the case for all I is equal to 0, 1, all the way up to k minus 1. So absolutely all of these quotient groups that you can construct once you've got your subnormal series must be simple groups, and if that is the case, then we call this subnormal series a composition series for the group capital G. Okay, so there is the definition of a composition series for a group capital G. Okay, so let's just give a bit of interpretation as to what this actually means. Why is that important? Why should we care? Well, let's just recite what the definition of a simple group is. A simple group, remember, is one where the only normal subgroups are the trivial subgroup and the improper subgroup. Remember, it does not mean that the only subgroups are the trivial subgroup and the improper subgroup, just that the only normal subgroups are the trivial subgroup and the improper subgroup. Okay, so if every single one of these quotient groups that we can construct between these subgroups in the composition series here are actually simple, then what does that actually mean? Well, now what we can do is we can apply the correspondence theorem. Remember, the correspondence theorem tells us that any normal subgroup in here will have a corresponding normal subgroup between gi and gi plus 1. So if I had a normal subgroup in here, this is what the correspondence theorem tells me, that if I had n bar, let's say, which was a proper normal subgroup inside of gi plus 1 over gi. In fact, actually, I'll just have it as a normal subgroup, more general. Okay, what it has that corresponds to it is it has a subgroup n, which is in between these two. So I'll write it like so. Okay, so here will be gi, and then you'll have this subgroup n, which will be normal inside gi plus 1. Okay, so this is what the correspondence theorem tells us. In fact, it works both ways. There is a correspondence between the subgroups of the quotient group and the subgroups that are in between the thing that you've quotiented out and the thing that you've quotiented out by. Okay, and in particular, of interest to us is that there's a correspondence between normal subgroups. Okay, normal subgroups here will correspond to normal subgroups here, and normal subgroups here will correspond to normal subgroups here. Okay, so just to make this concrete, the trivial subgroup here, that will correspond to this subgroup, gi here, which will evidently be a normal subgroup in gi plus 1. Okay, because gi was normal in gi plus 1 in order for us to quotient gi plus 1 out by gi. The improper subgroup here will correspond to gi plus 1, which is evidently a normal subgroup in gi plus 1. Okay, if you have a more interesting normal subgroup, a normal subgroup that is not the trivial subgroup or the improper subgroup here, it will correspond to normal subgroup that is properly in between these two, i.e. which is properly contained in gi plus 1 and which properly contains gi, okay, i.e. you can get rid of these is equal to bits here. So if this is proper, all of these become proper, assuming that this isn't the trivial subgroup. Okay, so what does this then mean? If we're saying that all of these are simple, then that means that there are no interesting normal subgroups. There's only the trivial subgroup and the improper subgroup, and that means that between these two there are no interesting normal subgroups. There is only gi and gi plus 1. So if I say that I have a normal subgroup in between these two, and these are involved in a composition series, then you can instantly conclude that there is no interesting normal subgroup in between these two. Okay, if you have got a normal subgroup in between these two, it has to be either gi or gi plus 1. There's nothing that's properly in between the two and which is a normal subgroup. Okay, so that's the interpretation of it, that you've got this ascending chain of subgroups that are all normal in the one above them, okay, and they are in a sense the biggest subgroup that is normal in the one above them. Okay, you can't find a larger normal subgroup that is still a proper normal subgroup that properly contains the one before. Okay, and that's what this is really saying. So there is an intuitive notion here. Okay, right. So what I want to do now is I want to firstly give you a little bit more terminology concerning composition series, and then what I want to do is prove that for a finite group there is always going to exist a composition series, and then we'll give some examples of actually finding composition series of certain finite groups. Okay, right. So firstly then, let's just have some terminology then. Okay, so terminology. So the two pieces of terminology that I want to introduce are the length of a composition series and also what is meant by the composition factors. And we're going to use this terminology continuously from here on in this video. Okay, so terminology then. So the length of a composition series. So this is an intuitive notion. Okay, the length of a composition series is defined to be the little k here. Okay, so it's reflecting the number of subgroups that you actually have in this composition series. Okay, now of course really you'd have k plus 1 if you counted the trivial subgroup, but you don't count the trivial subgroup. In a way, what you're really counting is the number of these quotient groups that you can form. Okay, so you can form 1 for gk, 1 for gk minus 1, 1 for gk minus 2, all the way down to 1 for g1, where you quotient out by g0, but you can't form 1 for g0. Okay, so you count how many of the quotient groups that you can form rather than actually how many subgroups are involved in the composition series. So it's 1 minus the number of subgroups that are actually in the composition series, and you can think about just not counting the trivial subgroup here. Okay, so there's the length of the composition series. Okay, so it will just be what's the number that's subscript on your G, which is equal to the entire group, the improper subgroup. Okay, right, so there's the length of a composition series, a very intuitive notion. And then the other piece of terminology is composition factors. Okay, so we've already talked about these, we just haven't called them the composition factors. So the composition factors are these quotient groups that you can form. Okay, so you can form k of them. You can form the length of the composition series composition factors. So all of the gi plus 1 quotiented out by the gi's. Okay, so you can do gk quotiented out by gk minus 1. That would be a composition factor of your group. You can do gk minus 1 quotiented out by gk minus 2. That would be a composition factor of your group, all the way down to g1 quotiented out by g0. That would be a composition factor of your group. Okay, so if you can find a composition series for your group, then you can split it down into these composition factors, and all of the composition factors are going to be simple groups. Okay, and this is why we can think of finite groups as being built out of finite simple groups, because as we will see that all finite groups do in fact have a composition series always. Okay, and we will also see that even though a composition series is not unique for a finite group, the composition factors in any two composition series that you build will always be the same, so that there is a list of composition factors for a certain group that characterizes that group. Okay, so each group has a list of composition factors that is, its list of composition factors. It's well defined, basically. So it is a well defined concept to take a certain group and talk about its composition factors. And that is why we can think of finite groups as being built out of finite simple groups, because we can break them down into their composition factors, and these composition factors will be finite simple groups. Okay, now, one warning to say here, that unfortunately it doesn't fully characterize a group. Okay, you can have two different groups that will have the same composition factors. Okay, so it's not the case that if you've got a list of composition factors that uniquely determines a group. Okay, it is true that each group has a list of composition factors, and that's the only list that you can devise for that group. So it's well-defined mapping to go from a group to its list of composition factors, but unfortunately it doesn't have an inverse. It's not a bijective map. Okay, multiple different groups can have the same list of composition factors. Okay, right, so there's some terminology concerning composition series. I think we'll have a break here, and in the next video what we'll do is prove that all finite groups have a composition series, okay, and then we'll do some examples of actually constructing composition series, and then we'll move on to the Jordan-Hӧlder theorem.